Okay, so now we've looked at, well, that things do decay and how they decay. Let's move on now to how quickly they decay and how this process happens. Because it's not just boom, it disappears, right? In some cases, it approaches that, but in some cases, it takes many, many years for a significant amount to decay. So again, you can bombard an atom with high energy matter, often neutrons, and if you get a neutron to stick in the nucleus, essentially you cause radioactive decay to begin because you've now made it unstable with too many neutrons. Okay, but as the ones we have mostly looked at, they just decay spontaneously. Now, what does it mean for something to be spontaneous? If you are a spontaneous person, you just do stuff, right? You just do it on your own. You don't need anyone telling you. In fact, you don't like people telling you. You just kind of do stuff when you feel like it, right? When you feel like it. That is what spontaneous decay is. Atoms just kind of do it. And it's entirely governed by probabilities. So, in any given moment, there is a probability that an atom is going to decay, but you can't say for sure, oh, that thing's about to decay, okay? So there's no way to determine when it will for sure, but that's the thing with probabilities. If you have a big enough sample, you can use probabilities to start to make predictions and start to notice patterns. That's why, like, where any survey you see, where, for example, the sample size is less than 100, it's probably a garbage survey, right? 100 people does not represent a very big population, unless you were doing maybe like the grade sevens at Father Merck. Okay, that would probably give you a pretty good picture, right? But you could just go pick 100 of your friends and ask them to give your exact opinion. So be careful for that when you see surveys. Same goes for scientific studies. If you ever see a sample size that seems low, that's probably a garbage study done by some company that has a new product and they want you to buy it. So they said, yeah, in the 3 mice we tried it on, they survived, right? So my point is, probabilities, if you get a big enough sample size, they really do start to become pretty reliable. So what's the probability of flipping a coin and getting heads? Well, it's 1 in 2, right? Or 50%. If you flip 2 coins, there's a pretty good chance you're going to get a heads and a heads, right? Or a tails and a tails. You really can't, I wouldn't put a lot of money on getting a heads and a tails and getting that, and getting exactly 50% of each, right? But if you flip 100 coins, probabilities are going to start to take effect. You probably are going to get pretty close to 50 heads and 50 tails. If you flip 1,000 coins, you're going to get pretty close to 500 heads and 500 tails. If you flip 1,000,000,000 coins, well, within a few decimals of rounding error, I would be willing to bet quite a bit of money that you will have about 50% heads and about 50% tails. Luckily, we're talking about atoms here, so for the most part, it's easy to get a big sample size, right? Unless we're talking about the more exotic, synthetically made elements. But essentially, the pattern that emerge allows us to determine something called an atom or isotope's half-life. The reason I say atom or isotope is, just remember, if it's bigger than lead, any isotope will be radioactive. If it's smaller than lead, it can still be radioactive. It just has to be the right isotope. So for example, hydrogen is definitely not radioactive, but hydrogen 4 with 4 nucleons is very radioactive. All right, so what is the half-life? It's just the time it takes half of them to decay. And the half-life is different for every isotope, but for the relatively common ones, the ones that we have a lot of or we can make easily and look at fairly well, we've studied their half-lives really well, and we know them with a pretty high degree of accuracy. Again, just the probabilities, but with enough atoms, those probabilities become pretty close to reality, right? Okay, just a note here, there are several ways to measure half-life. One could be mass, number of nuclei, or a very common one, because it can be difficult to know what mass is actually your parent, or even more difficult to count the number of nuclei. So a common way of doing it is just with activity, like radioactivity. So literally how many times it's emitting per second. Or I'll say emissions per unit time anyway. Because as you can see, we have tons of different kinds of units for activity. They all are kind of used in slightly different places because some things are going to be emitting thousands of particles per second, and it makes sense to use a different unit for those than for ones that might be emitting 1 particle every 10,000 years, okay? And so I'm just showing you all the units so that if you see them in a question, you don't go, what the heck is that, right? There's becquerels, there's curies, there's rads, there's rems, there's grays, there's sieverts. Most of them just deal with how many emissions per time. Some deal with emissions per time for volume or whatever, but they all boil down to the same thing. How active is this sample? And you can imagine if it's decaying, once it's decayed, right? So the activity will go down over time. They all essentially do the same thing though. They communicate the amount of the parent nuclei remaining. Okay, so to give you the idea here, okay, again, this is not a big enough sample size, but just to go with a nice easy number like 100, okay, so at the start, if 0 years have passed and you have 100 atoms, that's the original amount. Nothing's decayed yet, okay? So if you start with 100 atoms of some radioactive material, I can tell you this is carbon-14 because the half-life of carbon-14 is 5,730 years, but this number is essentially irrelevant for everything that comes after because it's one half-life. This will be the same no matter what the half-life is. It's just the half-life changes depending on the element you're dealing with. So after one half-life, if you started with 100, you'll have half of that. So you'll have 50 atoms, okay? Give or take, it's all probability based, and 100 is realistically not enough, but you get the idea, right? Now here's number one student mistake with this stuff. They say, okay, two half-lives. So if one half-life took away half, two half-life takes away the other half, and you have zero. No, 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 please don't ever say that. Remember, a half-life is the amount of time to end up with half of what you started with. What did we start with when we went to the second half-life? We started with 50. So after another half-life, we have 25 atoms because that's half of the half that we already had, right? So we're going to go half of a half of a half of a half of a half. Okay, it's not what you had at the very beginning. It's half of your new amount, right? So then after another half-life, after three half-lives have gone by, you can see this. These are just multiples of 5,730. You have half of 25. Well, you can't have 12 and a half atoms, so you probably have 12 or 13. Again, these are all based on statistics, so you might have 14, you might have 11, you might even have outside of that. But to the best of our predictions, based on probabilities, you should have about that. The more atoms you have, the more closely this will be modeled. After four half-lives, you would predict half of 12.5, which is either going to be 6 or 7, because that's 6.75, right? Now, statistics really start to break down when we get to this few, and then after five half-lives, when we now have 3 or 4, right? Really, probability is not going to work with this level of atoms. If you're flipping 3 or 4 coins, there's a very good chance that all 4 of those will just come up heads, and boom, your parent material will now be all gone, right? Maybe none will decay in a half-life. Maybe all of them will decay in a half-life. If you have a big enough sample size, you can predict fairly confidently that half will be left after each half-life. Once it gets too small, probability starts to break down. The same way, if you have a stadium full of 100,000 people, there's a pretty good chance that 1/12 of them are born in January, 1/12 are born in February, and so on, right? Because the probability of being born in any month is 1 in 12. So if you have a big enough sample size, those probabilities start to model what your actual observations are. But if I just walk down the street and pick out 12 people, it's probably not a great chance that one's in January, one's born in February, one's born in March, all the way through to December, right? It's not a big enough sample size for that probability to really express itself yet. You need more. And half-lives vary a lot. You can see here they range from 10 to the minus 24 seconds. That's the half-life of an isotope of hydrogen called hydrogen-7. Yeah, you can imagine 7 nucleons in a hydrogen atom. That thing's going to be pretty unstable, right? All the way up to 10 to the 24 years. How long is 10 to the 24 years? Oh, only about 160 trillion times older than the universe. No biggie. So that is obviously a very stable element, and yet we can work out its half-life using statistics. So this is what a decay curve generally looks like. And you could have tons of stuff on this axis. Like we already said, you could have number of nuclei, you could have mass, you could have activity. All are saying the same thing. They're all just ways of saying how much parent is left, okay? So you can see here time as a multiple of the half-life. Well, if you start with some amount, A naught, then at time 0, well, you have A naught, right? You have 100% of the original amount. After one half-life, you have 50%, or a half, right? After another half-life, you cut that in half to a quarter, or 25%. Then you cut that in half to an eighth, right? See, we're just dividing by 2. After another one, divide that in half to 16th, and then divide that by half into 32nds, okay? Now, important to note, the decaying element is not just disappearing, okay? It is transmuting into the daughter, into a different element. So the total number of nuclei stays constant. It's just that they're changing what kind of nuclei they are. If you flip 100 coins and 50 come up heads and 50 come up tails, you still have 100 coins. So this graph kind of shows that here. So they're only graphing parent. Notice like 1 half-life, 2 half-life, 3 half-lives, 4 half-lives. Notice the total amount of nuclei doesn't change. We just go from the dark red ones here are the parent, the light yellow ones are clearly the daughter, and so the total amount stays the same. It's just that the balance shifts from more parent to more daughter. Okay, so thorium-232 has a half-life of 14 billion years. So what does that mean? It means every 14 billion years, you're going to have half of what you had 14 billion years ago, right? So here we have years in billions. Each dot represents 0.1 million atoms. So we started with 1 million, right? After one half-life, how many should we have? 0.5 million, right? And we do. After another half-life, how much do we have? 0.25 million. After another half-life, we should have 0.125, right? And then divide by half again, we should have 0.0675. So this one was done in number of atoms. Notice I barely even looked, okay? Really, they all say the same thing. Still read your axes. It's a good habit. You always should. However, for the most part, they're all just going to be different ways of communicating the amount of parent left, either directly or indirectly. Okay, so consider this graph. What is the half-life of this substance? Well, the half-life is when you have half of the original amount, right? So how you can figure that out from a graph is just go, okay, find where I have half of my original amount. So I started with 100 becquerels of activity, and when half of that is left, I will have 50 becquerels of activity. So draw a line over and see how many half-lives have gone by when your activity is at 50% of where you started. And looks like it is 5 minutes. Be careful, read the axes for the time. If a scientist started with 8,000 centigrams, there's a unit you don't see much, of this element, how much would be left after 25 minutes? Okay, well, how many half-lives is that? 25 minutes is 5, 10, 15, 20, 25. That's 5 half-lives, right? So start with your original amount and divide it in half 5 times. Or you could think of it as 1 half, half, right? Just doing this 5 times. And yes, you're probably screaming, why don't you just put a power in there? We are going to, okay? It's just to give you an idea of why we're doing it. But I got that when you do that, I got that you would end up with 250 centigrams. Okay, so you kind of already know this formula, right? If you were able to think about that last question, you know this formula. But they gave you the formula in your formula sheet anyway. So let's take a look at it, okay? All we're saying is that the amount you end up with is going to be equal to the amount you started with times 1 half for every half-life that went by, right? So if 2 half-lives went by, it would be original amount times a half times a half. If 3, it would be times a half times a half times a half. And an easier way to do that is just to say 1 half to the power of how many half-lives have gone by. How do you figure out how many half-lives have gone by? Well, take the total time that's gone by and divide by the length of 1 half-life. So if it's been 4 years and a half-life is 2 years, then 2 half-lives have gone by. 4 divided by 2, right? If it's been 16 years, then 8 half-lives have gone by. 16 divided by 2. So this formula really makes sense, right? It's nothing spooky, physics, weird derivation. It's just saying, yeah, well, that's what a half-life is. So multiply what you have times a half for every half-life that goes by, and you'll figure out what you end up with. Okay, I will do the other examples in an example video, but let's do this one here because there's some theory mixed in, and we should do one example at least, okay? So if a sample of 2 grams of strontium-90, which has a half-life of 28.5 annum, just a fancy word for a year. That's where annual comes from. I think it's Latin or one of those things. Annum is just Latin for a year, okay? Is produced, what mass of strontium will remain after 1 annum, 1 year? So we can figure out how many half-lives have gone by saying, okay, 1 half-life is 28.5 annum, and it's only been 1 year. So it's been 1 year, and that is how many half-lives? Well, take it and divide it by how long a half-life is. So 1 year is only, right? And it shouldn't have units. The units are half-lives. If you want, you could say years per half-life, and then you would get that out. Okay, so that's it. That makes sense. It hasn't been a full half-life. It's actually pretty far away from being a half-life. So how many half-lives has it been? 0.035. So now we're going to say, okay, how much will we have? N is equal to how much we started with, N naught. And then for every half-life that's gone by, N, multiply it by 1 half, or 1 half to the power of N, in other words. So I got that you would end up with 1.95 grams. Easy way to check your work on all of these questions, right? You know what a half-life is. So if it's been more than 1 half-life, you should know that you'll end up with half or less, right? If it's been less than 1 half-life, you should end up with more than half of your original amount. We saw that this was not very many half-lives at all, right? So we're expecting not to lose that much, definitely not half, and sure enough, it checks out. So good, you can check your work on these pretty easily. Okay, review question from yesterday. If strontium-90 undergoes beta decay, what does it become? If it doesn't say what type of beta decay, I think I forgot to mention this yesterday. If it doesn't say which type, assume beta negative because it's much more common. So it becomes yttrium, right? That's the only thing with an atomic mass, with an atomic number of 39. All right, how much of this new product will there be in 1 year? Well, where is this new product coming from? Is it just poofing out of thin air? No, right? It's coming from whatever is gone from the strontium, right? Whatever is gone from the strontium is now yttrium. That's how this works. It's not disappearing. Strontium is becoming yttrium. It's not disappearing, right? We will still have 2 grams total of stuff. It's just now going to be a different ratio of strontium to yttrium, right? So if we had 2 grams total, we lost 0.05 grams of strontium, it became yttrium, or 50 milligrams. Okay, sketch the graph of the number of parent nuclei as a function of time. I'm going to put my time in half-lives, because why not? So after 1 half-life, if we start up here, we should have half of that, right? So just estimating. After 2 half-lives, we'll have half of that. After 3 half-lives, we'll have half of that. After 4 half-lives, half of that. After 5 half-lives, half of that. Something like that. Okay, on the same sketch, predict the shape of the daughter nuclei as a function of time graph. Justify your response. So let's do that one in red. Okay. So question for you, how much daughter nuclei did we start off with when it was all parent? Well, none, right? I just said it. It's all parent. So start off with 0. Okay, after 1 half-life, half of the parent is gone. Where did it go? Didn't just poof. It became daughter. So if half of the original parent is gone, half of the total amount will now be daughter. Okay, after 2 half-lives, a quarter of the parent remains, which means 3/4 of it is now daughter. Okay, then we have an eighth is parent. So 7/8 is daughter. Whatever is not parent is now daughter, right? A 16th, 15/16, and then a 32nd, 1/32. So 31/32 is now daughter. If you pick any point on these 2 graphs, so if you pick that point and that point, any vertical point where you go like that, and add them up, what percentage should you get of the original amount? 100, right? You essentially watch one bar graph go down while the other bar graph goes up. And why? Justify our response. So right, I'm just making up random numbers there, but those will always be true. It will always add up to 100. Okay, jumping a bit ahead, I'll do those examples in an example video. So far we've just said how much of the sample will be left. How do we actually use these to date things? Because this is how we date things. If you've ever heard someone say, oh, they carbon dated this fossil, or they carbon dated this ancient civilization's artifact that they found, right? That we're talking about radioactive dating. So you have to know the current activity, the original activity, the half-life of the relevant isotope, which for most of the common ones we know very well, okay? And technically you need some math from Math 30, but you don't need Math 30 for Physics 30, so we will not need it. You could do it. It's not too tough. It's just logarithms, okay? But because of that, questions in Physics 30 will always be worded to allow you to simply count the half-lives. So in other words, a nice integer number of half-lives will always have gone by in Physics 30. We sometimes call it the finger method because you count out half-lives literally just on your fingers. Okay, so how does it work? Well, pretty simple. Take the original activity and just start dividing it in half, right? So divide it by 2, literally just hitting enter, enter, enter on your calculator. Count on your fingers how many times you need to do this until you get the current activity, okay? And then what do you know? You've counted the number of half-lives, because every time you divide by 2, you're saying a half-life has gone by, right? Then multiply by the length of one half-life to get the time that has passed. Well, that makes sense. How many half-lives have gone by? How long is a half-life? Well, multiply those 2 numbers together and you've got the total amount of time that's gone by, right? So essentially, as units, you're saying number of half-lives times how many years per half-life. Okay, so let's just do one example. The other one I'll do in the video, the example video. Okay, so a fire pit is found in an archaeological dig. The carbon-14 isotope, which is what we use for carbon dating, in the ancient ash is 40 emissions per gram, while in the newly formed ash, it is 1,285 emissions per gram. How old is the site? So again, emissions per gram, don't get thrown off by that. It's just a way of saying how much material there is. The older it gets, the less it will be emitting, because as we've seen, there's less of the material to be radiating. So the chances of it emitting go down, and so the emissions go down. Okay, so literally we're just going to take 1285 and divide by 2, and that's 1 half-life, right? Normally, you wouldn't have to write out all this work. You would just do it on your calculator and count on your fingers, but you can't see me doing that, so I'll show you on the board. Okay, did that do the trick? Are we at 40? Nope. So keep going. Yes, this is our second half-life, but I'm just saying between here and here, one half-life has passed, right? So divide by 2 again. Nope, not there yet. Got to keep going. Nope, not there yet. Ooh, this looks good. One more, we should be there, right? So, and sure enough, bing, bing, bing. So what's left to do? Count up the number of half-lives. So we have 1 half-life went by, 2 half-lives went by, 3 half-lives went by, 4 half-lives went by, and 5 half-lives went by. You can always check yourself by taking the original amount now and timesing it by 1/2 to the power of 5 and seeing if you do indeed get 40. Okay, so now age, right? How many half-lives went by and how long is a half-life? Multiply those together. It's really just a unit conversion when you think about it, right? It's like saying, how many seconds went by this week? Well, how many days in a week and how many seconds in a day? Same idea. You can even check your units, though obviously these aren't standard units. Okay, and to 2 sig digs, that is about 29,000 years old. Okay, that wraps up the theory video. If you're looking for practice with this stuff, check out the topic 3 practice assignment in the Google Classroom or agenda. And then, like I said, I'll make an example video going through the ones that I skipped through.